So let's talk about Jupiter in the context of exoplanets for like 30 minutes or something, and then we're going to delve into the database, because you have access to all this data yourself. And you don't need me to filter this stuff out. You can just go in and start doing stuff with it. And there's lots of cool tools. And there's a ton of research projects. In fact, even so, cool research project I just learned about, we're going to talk about the Kepler Database. Right? The Kepler Database looks for planetary transits. And of course, planets are round. Unless you're a super intelligent species who has built a planet-sized object that is not round. Right? Could we do that someday? Could you imagine doing that? We're talking about building an occulting disk that's a couple hundred kilometers in size. So, right, you start to see maybe we could do this. So there's a proposal out there. Right, Jeff Marcy is looking for non-spherical objects transiting in front of stars in the Kepler database. Now the cool thing about that is this guy wrote this interesting paper. So, you know, triangle, square, Borg, whatever. Although if we were to build, I mean, the Death Star was round because it was just the easiest thing to build, right? Although not necessarily. I mean, if you build something, yeah. So somebody suggested that an alien species could use the power of the sun to communicate with other alien species by putting basically a Clax tower or a system of louvers in front of the star that you could open and close and do semaphore signals. Now, if you think about it, that sounds really dumb, but to transmit a signal to another star is really hard to do. The amount of power you need to do that is huge. But if you put this little shape around that every time it goes in front of the star, you just switch its configuration, that signal gets embedded in the transit of the object going around the star, and you use the luminosity of the star, which is seen across the galaxy in all directions, at least in that plane, right, to communicate with whomever you like. So if we wanted to demonstrate that we were here, we could build this device and have it circle our star and do this kind of stuff. So people are actually looking for this stuff.
I don't think any other alien races know Morse code.
Yes, that's true. They wouldn't know more. Well, so they do know primes. And so one of the configurations, if you were just simply trying to say, we're here, which of course, if you've seen the movie Battleship, you'd never want to do that. Never say we're here, right? Bud Collins called it the best movie based on a video game, or based on a board game. That's what he called it. But anyway, if you just wanted to signal you were there, you could just put like louvers that had 2, 3, 5, 7, and then those prime numbers would be embedded in the transiting planet. So. All right, so let's fire up some things about our Jupiter-class planets, and then we're going to move into the exoplanets here, if I can find out where this is.
Oh, I was doing some research and I found out, did you know the U.S. government actually has a plan on what to do in case of aliens?
Yes, yeah. In fact, I know the guy who is kind of he's called the NASA's Planetary Protection Officer. And if and mainly what he's concerned about is planetary contamination, like Andromeda strain type stuff. So if we bring back something from the moon and it's contaminated with stuff, then he comes into play to try and quarantine it. But if we did get abducted, or if we did have aliens come in and try to take over the planet, he would be elevated. Like, it's not in the Constitution, but he would become one of the leaders. Yeah. Planetary Protection Officer, yeah. He's a really funny guy, too. So if you ever want anybody to protect your planet, he's the one. All right, so let's spend a few minutes talking about Jovian planets, because these are the planets that we can see up close. And exoplanets are the easiest exoplanets to find are the big ones, right? At least to confirm their existence. We have to be careful the difference between detection and confirmation. Detection is we see a planet-sized object dimming the star or doing something to the environment. Confirmation is when you know its mass, because then you know the physical size of it. Well, I'm sorry. If you know the size, you know the physical size, but it could be a white dwarf, which is the size of the Earth but the mass of the Sun, and that's not a planet, right? Okay, so these are Jovian planets, and your textbook has a good description of why these guys exist as round balls. And these are a transition from our rocky planets, right, to stars. These Jovian planets are basically transition objects because we don't know, I mean, the difference between Jupiter and the Sun, what is the difference between Jupiter and the Sun? Temperature, yeah, which is determined by what? The size, or more explicitly the mass, right? If anybody ever read 2010, the Space Odyssey 2 by Arthur C. Clarke? See the movie? Breaking my heart here. Well, your next assignment that's due Thursday has this. You're going to have to watch the movie. HAL 9000, do you know HAL 9000? 2001, Stanley Kubrick. It's a classic movie. Have you seen Gone with the Wind? You have. Have you seen 2001? Okay. Have you seen 2010? Damn it. Okay. Fix that as quickly as you can. Go watch 2010. It's probably on Netflix or something like that. Have you seen it?
I haven't seen any of them.
You work in a planetarium. How can you not? You should have a library of these things. Wait, let me tell you the story. So, recap of 2001, right? Monkeys are on the Earth. Well, they're apes, really. Before they evolve into Homo sapiens, they uncover a monolith, right? That teaches them how to use tools. So this is the mythology of this movie, is that there's been an alien species kind of guiding our progress, right? So flash forward to 2001. Of course, we're in space. 2001. Of course, we'd be in space. We're on the moon. We've got Mars bases. You know, it's 2001. It's the future. Anyway, they unearth another monolith on the moon, which sends a signal to Jupiter. So we build a spacecraft to go to Jupiter. Right then, 2001, we do it. No problem, because it's 2001, it's the future. And we send the probe to Jupiter. Jupiter interacts, or the people on the spacecraft have a robotic intelligence, HAL 9000, artificial intelligence, that then goes crazy because it becomes self-aware, but he's a robot. Anyway, it's very dramatic. He kills everybody on board except for Dave Bowman. Dave Bowman meets aliens, transcends into a new type of creature that then goes back to visit the Earth as the next stage of evolution of Earthlings, of humans. Okay? So that's that movie. I ruined it for you. You don't need to watch it. 2010, right? 2010, NASA notices that, because of course the spacecraft they sent out there in 2001 is still orbiting Jupiter, but its orbit begins to change and decay. And as you know, the change in orbit indicates a change in mass of the system. Something's going on out there. So we send another probe, 2010. It's future. Second human mission to Jupiter by 2010. Okay, we send this 2010 mission to Jupiter. They get there, and you'll have to watch the movie. But the punchline is, at the end of the movie, am I going to ruin this for you? You okay with this? This is a spoiler alert. At the end of the movie, the aliens change the mass of Jupiter they dump a bunch of mass on it to turn it into a red dwarf star. They didn't have to dump that much mass on it to do that. Big monoliths. They flew them in from, yeah. You have to see the movie, read the book. My point is that the difference between Jupiter, if you took Jupiter and dumped a bunch of mass on it, it would turn automatically into a star. Because the gravitational contraction would require it to get hotter and basically start fusing hydrogen into helium. So I wanted to just quickly run through this calculation about the hydrostatic equilibrium that keeps Jupiter from doing this, but it also indicates what would happen if you were to put more mass on there. Okay, so these are gas giants, which means we can write down the equation of state for these planets. They're basically big balls of gas, right? And the equation of state is given by something called hydrostatic equilibrium, right? And what does hydrostatic equilibrium mean? Didn't we talk about this already once? In your physics classes, when I say hydrostatic, what am I talking about? Hydro means fluid, yeah, water. Static means not moving. Okay, so we can treat it as a fluid, and it's not moving. Jupiter is not getting any smaller or any bigger. Okay, so there's two forces competing here. One is the pressure force pulling down. The other one We've done this before. I think we did this already.
Oh, yeah.
Yeah, we did this, right? So we've got, you've got the gravity pulling down, Fg, you've got pressure from both sides pulling up. This is delta R, so we don't need to do this calculation again. I can write down the result that we had the pressure gradient, dpdr, is equal to minus gmr, which is the mass enclosed of where we are in this planet, times the density divided by r squared. So that's our hydrostatic equilibrium condition. The mass enclosed, now in this case we don't necessarily want to assume a constant density, but you can. So the mass enclosed, if we don't assume a constant density, is equal to 4 pi times the integral from 0 to r of rho of r squared dr. Right? So this is just 4 pi r squared, which is the surface area, times the integral of dr over the density. So this gives you a mass. And if you assume that rho of r is approximately constant, which it isn't, but if you assume that it is, you get that the mass enclosed is just 4/3 pi rho average density cubed. And I can take that and plug it in there and do the integral, and I can calculate the density I would expect to find at the core of this planet. Right? So let's go ahead and do that. If I go ahead and plug that mass in there, I'm going to get dpdr is equal to minus 4 pi over 3 rho squared, because we get a rho, two of these rho bars in here, times g times the integral from 0 to r of r dr, because I'm going to lose an r squared and an r cubed is going to turn into r, right? Don't have much board space here, but that's all right. I'm not going to do this for very much longer. So if I do that integral, I get the pressure at the core is equal to 2 pi over 3 rho bar squared g r squared. And that gives us an estimate, a first order estimate of what the pressure at the center of these things are. And for Jupiter, that pressure turns out to be about 10 to the 7 atmospheres. And for Saturn, this is Jupiter, for Saturn, that turns out to be about 10 to the 6 atmospheres, which is not enough to fuse hydrogen to helium, right? But if I wanted to fuse hydrogen to helium, all I would have to do is basically increase the mass enclosed. And I can do that by increasing the density or increasing the size, just adding more material, right? And once I do that, I can increase those densities. So the astrophysical question, the thing that people are asking as researchers, is where is the break between a planet like, you know, Neptune, Uranus, Saturn, and Jupiter, and a star like the one that was created in 2010? Where's the transition between that? And the answer is we don't know. Are these different formation processes? Why don't we have a binary star in our system? Most other stars do. Right? What happened? What do you think happened when Jupiter formed that kept us from getting a secondary star? I don't know the answer to that. If you know the answer to that, this is a research question, because it's fundamental to astrophysics, right? What is the formation process for stars, and where does that transition into planets? Is it the same? Did we just get unlucky that we don't have a second planetary system? Because as you will find in your assignment, we would have another planetary system if Jupiter was a star, with its own habitable planets around it, right in our star system. Wouldn't that be amazing? We're so unlucky that we don't have that, right? Or is it completely impossible for us to have that because of the way Jupiter formed? I don't know the answer to that. So when we look at exoplanets, we have to be careful about you know, these objects, because where something is a star or a planet depends on some things we just don't know about. So we generally say a star has to be fusing hydrogen into helium at its core to be a star. That's the definition of a star. But there's a gray area, because what about brown dwarfs that are fusing deuterium into helium? So they're skipping the first step. It's not hot enough to fuse hydrogen into helium. So I'm going to let me write this down over here, so I'm sure all my planetarium students already know this stuff, but if I, well, let me put it over here. So tell me the proton-proton chain, planetarium folks. The abbreviated one. 4 hydrogen goes into, that's the abbreviated proton-proton chain. Yeah, it goes into 2 of them. Now the real process, because you're never going to get 4 hydrogens to impact each other, right? That's just statistically improbable, right? But you have to get a helium nucleus has 2 protons and 2 neutrons, so you need 4 particles to make a helium nucleus. So what happens is you have 2 hydrogen protons effectively smack into each other. That can happen. That makes deuterium, right? Which is a neutron and a proton. So this is a deuteron, we'd call it. So we call that a deuteron. That happens twice. Someplace else in the sun that happens, right? Those 2 deuterons smack into each other and make helium. Sorry, no, I got it wrong here. That deuteron, because I mean, where are you going to get this other deuteron? That deuteron gets smacked into by another proton. Let's do it this way. Making a helium-3 nucleus. Helium-3, helium-3, and then there's enough protons around. If I smack this in with another proton, I wind up with a helium-4, which is 2 protons and 2 neutrons. There's a conversion process, and I wind up with helium-4. Fusion, okay? What if I am not hot enough to go from this step, but I am hot enough to go from this step? Am I a star? I'm fusing. What do you think? All in favor of deuterium fusing objects to be a star? Say aye. Aye. Opposed? Abstained? Right? We just don't know, right? What's the debate here? Yeah, I think it's open for debate where the boundary is.
Pluto's not a planet, those aren't stars.
All right, I'm with you. Yeah, so brown dwarfs. Well, we do have a designation, right? There's brown dwarfs. You could argue are failed stars, just like Pluto's a failed planet. It's a dwarf planet. Whatever. Interesting note, though, there is no definition of planet outside of our solar system. The International Astronomical Union's definition of a planet only applies to our solar system. So
how do we have so many confirmed exoplanets?
Because they're exoplanets. Yeah, they're just not planets. So if we found a Pluto around another star, we could call it an exoplanet, and nobody can say anything about it.
So they're not in the cool club?
They're not in the cool club. Yeah, they're not. Yeah, the planet's a very exclusive 8-member club. Yeah. All right, so some properties here: Jupiter, Saturn, Uranus, Neptune. You can read those properties here. The important thing is they're roughly the same, although I think it's interesting that the density of Saturn is significantly less than the others. The density of Saturn is less than water. You know my great joke? Did I tell you my joke about Saturn? Okay, I won't tell it again then. You must not have been here.
I don't think I was here.
Well, you need this. You work in a planetarium. You want to tell her the joke?
How do you know Saturn?
How do you know Saturn is less dense than water?
Leaves rings in the bathtub.
Yeah, leaves rings in the bathtub because it floats. Yeah. All right. Okay. All right. So I don't want to go through all this because this is mostly for my astronomy class, but I do want to show you this because it gives us some interior description of what Jupiter looks like. If you take this hydrostatic equilibrium and you do not do that assumption, the approximation, remember the approximation we made was that the mass interior was equal to 4 pi times the integral of rho of r, r squared dr from 0 to r. If you do that integral, if you basically do it the other way around and try to model the pressure as you go down, you can get the density as a function of depth. And if you model this, which would be another fantastic research project, especially someone trying to get their Mathematica skills back up to speed. Oh, by the way, let me just step aside here. Nobody did well, very few people did. You didn't even turn in the questions for your awesome thing. You got to turn that in.
Did you?
No. Yeah, I know you've got them. What's that? Oh, well, anyway, maybe I overlooked them. But you did the awesome app thing. I know you guys worked on the Mathematica thing, so get it done. It's very important because you're going to have to use it for this assignment this week. So you might as well go and do it, and then hand it in. And I'll look and make sure I don't have that sheet floating around someplace.
I'll look too.
Yeah. But anyway, get that done because you're going to use it again. Mathematica is awesome. All right. So modeling. If we come back and model this, you could do this in Mathematica if you wanted to. We can get the pressure gradient as we go down, and you can kind of see how the pressures increase. And let's look at our atmospheric pressure here. This is modeled 1 × 10⁸, and over there it says 10⁷, so not bad. Our approximation of constant density gave us, off by only an order of magnitude. But you can see the temperatures down there too, 20,000 degrees at the core. Here's the size of the Earth for comparison. And again, what is the stuff as we go down? We can only say because we understand the properties of matter in the laboratory, and we can predict what's going on down there. So we have gaseous hydrogen, liquid hydrogen, metallic hydrogen. As we go down, metallic hydrogen is a description of matter where we have a very dense ionized gas. So it's not a bar of metal made of hydrogen. It's ionized, high-density hydrogen. And so because it's ionized, its electrons are free. If you could make wires out of it, it would be very conductive. So they call it metallic hydrogen. But it isn't really metallic in the way that you normally think of it. Okay, so that gives you an idea of the pressures and temperatures as you go down. You can't observe that stuff. And so the observations that we're going to be seeing as we go out, let me find my little picture here, down here. Where is it? Oh, I know I have it. Yeah. So the observations of the planets look like this, right? These are observations of Jupiter. As we go to look for exoplanets, eventually someday we may take pictures of them that look like this. Or at the very minimum, we'll get 1 pixel on a camera that is the integrated light from all of this complex stuff, right? And so a question that a lot of the people are working on in astrophysics research is, why does Jupiter look like this and Saturn look like this? They're all made of the same stuff, right? And what would that look like from a distance? So can anybody give me an idea of why Jupiter has all this fantastic detail and Saturn doesn't? If we think about it in terms of the temperatures and pressures in the atmospheres, as we go down, what happens to the pressure and temperature in the atmosphere? Pressure increases, temperature increases. Okay. So let's take Jupiter, for example. Jupiter has mostly hydrogen and helium. It also has a bunch of other stuff, ammonia sulfide, ammonia, water, right? If you think about it on Earth, if you start at the top of the atmosphere and start going down, temperature and pressure increases, right? Eventually you get down to a level where what happens to the water in the atmosphere? What's that?
It's always liquid or it's always gas?
Right. So there's, if you have water vapor in the atmosphere and you get down to a certain point where if the conditions are right, we form water droplets, which are clouds, right? So as you drop down in the atmosphere of the Earth, going from the top of the atmosphere to the surface, eventually you reach a point where you can form clouds. You can't form clouds lower than that, usually, and you can't form clouds higher than that. So what you're seeing is the place where different materials can condense into clouds as you go down. And if I were to draw what that looks like, if I think about the atmospheric profiles for planets that we talked about before, if I draw, here's a graph of, let's say for the sake of argument, temperature, or sorry, let's make this height, z, and this is temperature. As I go down in the atmosphere, the temperature increases to first order, right? So I'm going down in the atmosphere, boom, boom, boom. Let's say I get to a place where the temperature is 273 degrees Kelvin, and I can condense water out for sure. Pressure is 1 atmosphere. Do we form clouds at this layer? Can you form clouds when you get cold enough? Right? If you're hot enough, do you get clouds? No, but if you get cold enough, you form clouds, so you get water clouds. Whoop, right? H2O. Well, these other clouds have different levels, right? You could form maybe ammonia sulfide at this level. That's NH4SH. There's some other ones like ammonia. That's NH4. Right? And there are other ones. They all form at different heights based on the properties of the molecule. right? And so if you're higher than that level, you don't get that cloud. If you're lower than the level, you do. So presumably all this stuff is in Jupiter's atmosphere as well. But if you look over at Jupiter's atmosphere, sorry, in Saturn's atmosphere, you don't see the clouds. You just see these bands. So my question is, where are the clouds? And why don't we see them? And I'll give you a hint. Jupiter's further from the sun. They're deeper, right? Because what does the temperature profile look like for, sorry, Saturn is further from the sun. Jupiter, look at this, Saturn's further from the sun, so it starts at a colder temperature to begin with, right? So you have to go to a deeper, right? You're lower down. I mean, let's see, how do we do it? We have to go, the H2O clouds on Saturn are over here, right? You have to go deeper to get to the same temperature to get the H2O clouds. So they're deeper into the atmosphere, which means there's more optical depth in the way. So you just don't see them. All the colors are there. If you look at Saturn, you know, Saturn versus Jupiter, all the same colors are there, but they're just deeper into the atmosphere. And I bring all this up just because as we start to look at extrasolar planets, or exoplanets as they're sometimes called, the structure of the atmosphere, the structure of the planet is going to impact what those planets look like. And these are the first planets we're going to see. In the intervening decades, between now and when we discover life on another planet, the first picture of an exoplanet you're going to see will be a Jupiter or a Saturn. And even though we won't see a picture necessarily, we might see a pixel that has a planet in it. And you know, how would you tell the difference between these two if you just had a pixel? Would you, I mean, are all the colors the same?
Well, those CSI TV shows can inflate those resolutions up to C values, so they can probably extrapolate what the planet.
Yeah, and if we just have one of those blue lights, you know, we just shine it on the thing there. All right. So, yeah, and blood. There you go.
We found a new planet, and someone has been murdered.
There you go. CSI Gliese 581. Okay, methane on Uranus and Neptune, why are they so different? Uranus and Neptune are the cool planets. These are the planets everybody wants to study. Just like we study Jupiter and Saturn because they're the transitions between stars and planets, Uranus and Neptune are the transitions between Earth and Jupiter. Right? So what makes a gas giant? Well, we can tell just looking at Uranus and Neptune, they're blue and green, so they clearly have something different going on in their atmospheres. And primarily that's a lot of methane mixed in with the hydrogen. Why is there so much methane in the atmospheres of Uranus and Neptune? Does it have to do with where they're formed? Could be, right? Could be that's why there's so much methane in the atmosphere. It could have something to do with how they differentiated. Right? Maybe there's a larger icy core at the center. Maybe there's a larger source of methane someplace. Would Uranus and Neptune look like this if they were at 1 astronomical unit, as opposed to out where they are at 40 astronomical units? What do you think? Would they look the same? Who says, all in favor of them looking the same at 1 AU, say aye. Opposed? Nay, right. So when we look at our solar system, we look at our solar system that looks like this. We have a lot of work to do because we're finding massive objects like these guys. But yet we're finding them at Mercury's orbit. So are they Uranus and Neptune, or are they something else? Now, there's a couple questions you should be asking yourself. First of all, how in the world do you get a gas giant? And it is a gas giant. We've got measured radii and masses. We know their densities. How do you get a gas giant in the orbit of Mercury? Or worse, with a 4-day period, which is what some of the exoplanets have.
It's got to be shaped.
Well, they probably has a huge tidal, and some of them have very eccentric orbits, so they must have very strong tides. So how do we get them in there? Any ideas? I have an idea, which we can model. Whether or not it's true or not, we don't know, because we don't have any migrated planets in our solar system to use as an example to study. But one of the models is that as you're forming planets in a disk of dust and gas, they interact with that gas, and there's a torque on them that pulls them in, right? Interesting thing about that, if you apply that model to our solar system, Jupiter and Saturn must have moved in significantly, like to the orbit of Mars, and then moved out again to be where they are. It's called the grand tack A lot of people think it's a really ridiculous notion, because how on earth do you form Earth and Mars if you bring these planets in? However, it's a great explanation for why Mars is so small, right? Because if you were forming Mars and suddenly Jupiter came in, that might cause some problems with planet formation, right? But again, we don't know. These are totally open questions. So the thing that's important about astrophysics today is that for the first time, we have a collection of objects which is starting to approach statistical significance, right? I mean, up until today, pretty much, we've been studying and basing everything we know about planet formation on 8 planets plus Pluto, right? Now we have 900 plus 2,500 planets, and even your textbook has it's 3 chapters on our 8 planets, and then 6 pages on exoplanets. So I would like to change that. In fact, before we even talk about solar system formation, I want to look at the data. So your book does this. Your book looks at 8 planets. This is the data. Now we're going to talk about solar system formation. I don't want to do that. I want to look at all the planets, and then we'll talk about solar system formation. So what I'd like you to do, if you don't have any questions about this stuff, I want you to fire up your computer. And we just need a web browser for this. And I'm going to show you a tool that you can use to basically do this exploration yourself. Yes. Now, while you're pulling this up, I just want to make a couple of remarks about this, because you'll notice I said there were 800 planets, and this says there's 673. What do you need, Narita?
Just big for the bridge.
Oh, okay. It is, but why is there a difference?
Thank you.
Well, I'll tell you why. This is, there's another site, and I'll give you the web addresses for these in a second. There's the European site, Encyclopedia of Exoplanets. Whoops. Oh, right. There we go. Okay. Whoops, what happened there? No. There we go. Okay. So there's 2 sites. And you can go to either one of these sites. I'm going to show you both the web addresses here so you can pull up both of these. And you should explore both of them. But there's the European exoplanet site, and then there is the US exoplanet site. And just to give you a little bit of a background on this, in 1996, the first exoplanet was discovered by Michel Mayor and Didier Queloz. They were Swiss scientists who were really stellar astrophysicists. They were looking for high-mass binary star companions with super short periods, right? They did not expect to find Jupiter-mass planets with 4-day periods around stars. But they found them because they were looking for short-period objects. However, in the United States, Jeff Marcy and Steve Butler were searching for planets, Jupiter planets with 11-year periods. He worked at San Francisco State University because universities like Weber State and San Francisco State are the only places that will let you perform work that takes a decade without publishing, right? Because they don't let you do that at Carnegie or Berkeley or anything like that. So anyway, so Jeff Marcy and Steve Butler are looking for Jupiters. They have the instrument that can do it. They're doing the detection for Jupiters. They're not finding anything because they have to wait 11 years to get one detection, and they have to wait another 11 years to confirm it. So they haven't found anything. And they're not looking for short period planets because they'll never see Mercury. It's too small. So Didier Queloz and Mayor found the first one. It was called 51 Peg, 4-day period. That really made Jeff Marcy and Steve Butler angry because they were the planet hunters. These other people just picked it up by accident. So they immediately found the next 90, right? But ever since then, there's been this tension between the European teams and the US teams, right? Because the US teams are very big on the accuracy of their catalog. There's no planet in the catalog that hasn't been confirmed through multiple observations in the literature, okay? The European folks are like, hey, did you find a planet? Let's put it on the website, and then if we confirm it, great, we can always take it down. It's the web, right? So the European site reports 800 and some. The US site reports 673. So if you really want to see what's the cutting edge of reported stuff of all possible things, you go to the European site, because they put everything in there. I mean, you could call them up and say, I found a planet. They put it in, and then they'll take it out when you don't get it published. The US site is much more for fundamental research because all of these have been vetted. And frankly, when there were only 12 known planets or 50 known planets or 100 known planets, that was a problem. Because when you've got 50 planets in the US and the Europeans are saying 75, 75 is a significantly larger data set. And you want to use more planets, but at the same time. But now that we're getting up in the hundreds, you know, use the ones that are vetted, wait for the other ones to get factored in. So it's kind of just two different takes of the same sort of thing. But this gives you the statistics for what we have. There's and this is funny. They're even making a distinction here between planets with good orbits listed in the Exoplanet database and confirmed planets that include microlensing and image planets. So these are planets that we don't have orbits. We just have masses or some other information about. So these are 673 with really good parameters. This is the total. And then these guys are unconfirmed planets from transits. And we'll talk about that a little bit on Thursday. But these are transit planets. In other words, you're just looking at their size. So these things, you know their size. These things, you know their orbits and their masses, and sometimes their size. These things, you might know their mass, but you don't know their size or their orbits. But we get total planets 3,300 if you look at all those things. Now, is everybody at this website, exoplanets.org? Yes? Okay. So there are two ways to explore this. The first one I want to do is plots, and then we'll come back to the table here in a second. The plots are nice because it lets you see any property you want, you can plot one against the other, and you can export things and do whatever you like here. So the way you can use this, first of all, there are some example plots for some common things that people do. So for example, if you wanted to look at the probability distribution of periods, so how many planets have the same period, I can just click on that and it should show me a histogram, which is showing the orbital period in days, and then it's showing a histogram giving me the number of objects that have that. And then there's a couple of, I don't know what these yellow, yeah, these must be the hot Jupiters. I don't know what these yellow things mean. Let's see. Oh, here we go. Yeah, hot Jupiters and then Jupiter analogs. So if we look at this, zoom in. You can zoom in on these things. The hot Jupiters are things that are considered very, very close and massive, right? So these are things with shorter than 10-day periods. My goodness, right? Now there are other ones that don't have the mass of Jupiter. That's why they're overlaying this. So these guys up here are not hot Jupiters. They're hot Uranuses, hot Neptunes, right? These are Jupiter analogs, in other words, things that have Jupiter period type orbits. So we are just barely starting to see Jupiters after 2 decades of work in exoplanet research. Just starting to see the Jupiters. Now some other things that you can explore here. There's orbit distance distribution, so what do their orbits look like? And I think this is pretty fascinating because this is what we call a bimodal distribution. Right? And what's fascinating about this is you have to remember, larger than 10 astronomical units, we haven't been looking long enough to see. It's only been 2 decades. So we're just now getting the second confirmation period on an 11-year orbit. So there's this right here is a real signal in the data. So those are planets that we're discovering because they're there, not just because they're easy to discover. This stuff we're not seeing because we haven't been looking long enough. Why is there this huge spike at close in? Are there literally more close in planets than far away planets? Or is there something else going on? They're easier to see, right? With this method, right? We see them more often, right? They're easier to confirm because they have 10-day periods or something like that. And so it'll be interesting to see how this distribution shakes out. What's interesting, though, is that we're now getting to the sensitivity, especially with Kepler, where we can try to see if this is a real spike of real planets or if it's just because we're more sensitive to them. And it turns out it may be a real spike. It could be that this really is bimodal distribution of planets, that there are systems like ours that have massive planets far out, and then there are systems like hot Jupiters that have massive planets close in.
So the second spike, so that's pretty much, I mean, obviously we don't know if it's a spike yet because it could just...
Right, it could just be, yeah, going up like that.
That's pretty much the Hubble right there.
Yeah. Now, these are not Earth-sized planets,
okay.
but yeah, this is pretty much the habitable zone, which, see, that to me, if we go back to the, let's do the orbital distance, or let's do the probability distribution for periods, right? So this is the habitable zone, effectively, right? Oh, wait, the next one over. Can I click on that? Will it do anything? Oh, it will. Ha! I love this tool. This is awesome. So if I click on one of those bins, it shows me all those planets. And if we look at, these are all things that have about habitable zone type periods, and look at their masses. They typically are Jupiter mass planets. So this is worrisome to me, because if there's a whole host of planets out there with a Jupiter sitting in the habitable zone, that's a problem. Now, one of your assignments is going to be to figure out exactly how many Jupiters are in the habitable zone, because they might have moons in the habitable zone. And it could turn out, and I just want to throw this out there, could turn out that habitable moons are more common than isolated habitable Earths. Because if it turns out that Jupiters are more common in the habitable zone than Earths are, maybe we're some rogue system that never migrated, right? Or we're a broken system that we have this crummy little rock that we live on. It's not even really that good for life. It's got this barely enough water for anything. It's junky. Whereas in other systems, you've got this massive Jupiter planet with 12 moons. 4 of them, all the moons are in the habitable zone. They all have life on them, right? Can you imagine this? It could be totally different. All right, so let's see what else we've got here. We've got, here we go. Orbit eccentricity versus semi-major axis. This is another thing that was a shock, right? Because look at our solar system. Our solar system, if you look at the data, we have 8 planets with almost circular orbits. Jupiter and Uranus, Neptune, Saturn, Earth, Venus, Mars, all circular orbits, more or less. Pluto and Mercury, not so much. Here are planets, most of them Jupiter mass or larger, with eccentricities of 0.8. So imagine living in this system. You have a habitable planet in the semi-major axis of 1, and Jupiter comes flying by like a comet every year because it has the same semi-major axis, so it has the same period. It has an eccentricity of 0.8. Right? Could that even happen? I don't know. But you've got Jupiter mass planets with eccentricities of 0.8. That's like cometary eccentricities. By the same token, if you're a habitable planet, could you be a habitable planet with an eccentricity of 0.6? Like imagine if Earth had an eccentricity of 0.6, and you can calculate, you know how to do this now, the perihelion distances, right? If you do an eccentricity of 0.6, if we start at 1 astronomical unit, right, the perihelion distance is equal to a times 1 minus e, so that's a times 0.4, so 0.4 AU, that's halfway between Mercury and the Sun. So if you have an Earth with one of these things, it gets twice as close to the Sun as Mercury, even though it has a semi-major axis of 1. What's up?
I think my brain is just
Why? What did I do it wrong?
Well, I guess I'm confused in how 0.4 can be halfway between Mercury and the Sun.
Because Mercury is at, oh, sorry, between Venus. Venus is at 0.8. I misspoke. Yeah, thank you. See, it's good to have you in here. Yeah, Venus. But still, Venus is at 8 or something like that. Ah, right. Mercury has an 88-day period. Right. So, but seriously, halfway between Venus, what would that be like? Would that be like Game of Thrones or something like that? You know, you come in and have summer, blowtorch for 30 days, and then you go out, frozen wasteland for however many 8 days that is. All right, so you can start to do these types of things, and you can do anything you want. If you choose X and Y, you get a whole list of every single thing that you don't even know what it is, right? There are tons of measured parameters for these things, and so you can select, for example, let's see here, stellar parameters, orbital parameters. Here you go. You could, if you wanted to, plot the mass versus, well, here, let's do this. Mass versus orbital eccentricity. This is interesting, right? So here's the masses. Here are the orbital eccentricities. Again, most of the planets with high eccentricity are low mass, but those are in Jupiter masses. So we're not even seeing, this is between 0 and 5 Jupiter masses. These are Jupiter planets. Now if I can make these, I think I can make this a log-log plot. Pretty sure I can. If I go down here, there's got to be a way to make it log. Marker scale, advanced. Yes, there we go. You can put error bars on, logarithmic color scaling, logarithmic marker scaling. Is that it? No, marker.
Turn off auto scale.
Oh, turn off auto. Did that do it? No, it needs. I'm looking for logarithm. That's the color scale. Data. Oh, here it is. Right. So I can put this on a log-log plot, which is a little bit easier to see, because you can see that there are still Jupiter mass planets with very high eccentricities. So the plan for the next couple of days is we're going to wade into this data set. Now on Thursday, I have a little introduction for you about how we find all this information out. But then we're going to wade into this data set. And before we go away for the day, and I want to give you some time to just play around with this yourself, I want to look at the table. And by the way, for those computer science students who are interested in astrophysics, this type of work, data mining and data display and data visualization, is huge. Large fractions of their budget goes to this sort of stuff. So if you get a kick out of this, that'd be a good career option. The table is interesting because it lets you do filters, right? So you can select a filter, and I can say, for example, if I want to see all of the Jupiter mass planets, right, I can say filter on m sin I. I can say less than 1.0, and that should have filtered, yeah, for all the Jupiter planets less than 1. Jupiter. And so you can put filters in there to select out different things that you want. So if you wanted to, if I asked you a question, how many planets are in the habitable zone, all you need to do is figure out, using your climate model, right, what's the width of the habitable zone, and then put those filters in there on the distance of the semi-major axis, and you can do that. So the cool thing about this tool is that it's very easy to use just to get some kind of general stuff, but it's also very powerful. You can also just download the whole data set and do whatever you want with it, right? So there's no reason why you're stuck with this tool. But this is what we'll be using in class for the next little bit. And let's see. Yeah.
What format does it download the data set? Can you choose?
Just a CSV file.
Oh, yeah.
It just gives you a huge data dump of every single column, all the data points. Yeah. And then you have to figure out how to cut it and dissect it the way you want. The thing I really enjoy about this, and this is new, right? So if I were a student and I were interested in doing astrophysics research, the most daunting task is wading into the database and writing your own code to analyze the data. You don't have to, right? They've got it. Now, there's another set of this here I guess I wanted to point to, is the Kepler data. And that one is a little bit trickier because, let's see here, I'll go to the Kepler database. There's not as much information, but you have access to 2,700 objects with at least you know the semi-major axis and the size. And so you can go into the plots of the Kepler data and see what Kepler has found. And this is new. I mean, this has been in the last couple of years. So we can do the mass, let's see, what did we do? Period. There was one probability distribution of periods. This is now for the Kepler. Oh, I am still. Where do you see that? Oh, or. Oh, there we go. Yeah, sorry. There we go. There we go, Kepler Database. Let's print that again. There we go. Oh. Huh, how weird. Well, I guess I'll have to zoom out. So let me zoom out. There we go. So this red part, oh, is that the habitable zone planets? Yeah, I think so. No, that's not it. Here, let's do this again. Well, let's do orbital distance distribution. That'd be easier. Okay. Kepler. Okay. So this is just the Kepler data now. And Kepler, again, has been flying for 4 years. So remember, science works by repetition, right? 1 year for the Earth gets you a detection. 2 years gets you a confirmation. 3 years gets you a publication. It's been in orbit for a little over 3 years, a little over almost 4 years. We're just now getting to this point where they're analyzing this data. So this number is going to come up as they analyze the Kepler data. So this distribution really should look, right? Now Kepler's defunct now. They'll have to fly another one to continue it. But this gives you an idea of what's been discovered in the Kepler database. So we just now got to the habitable zone with Kepler. Again, the information is not as, there's not as much information. We don't have mass, but we do have distance and size. So if we look at the Kepler database, we can look at, do they do the size distribution? No, we're going to have to do that one ourselves. So let's do a histogram plot of the size. Distance, orbital parameters, period, eccentricity, m sine I. Do you see size? Transit depth, no. Planet radius, there we go. Right. Have to get rid of that. Okay, so this is even more interesting, right? These are Jupiter radii of planets. And what is the Earth's Jupiter radius? What's the Earth's radius in terms of Jupiter's radius? Oh, am I going to have to do all the work here? What is radius of Earth? So you can do it faster. Radius of Earth in Jupiter radii. I think it's 1 over 300. That's what I'm going to go with. Mass radius. Earth. No.
Well, Jupiter over Earth in radius is 1. So just hit 1.312 inverted.
Oh, right here it is. Yeah. Here it is. 1 over that. So what's 1 divided by 318? 0.003. Okay, so if we look at this, 0.003 is right here. So we found 3 objects that are Earth size. Doesn't it say 0.03?
0.003.
Oh, well that's not right. I know we found objects. I know we found more objects than that. Logarithmic bins. No, I want logarithmic. Well, anyway, you're going to have to do this research next week. Because, oh, there we go. Yeah. No, that's still showing. Well, anyway, you'll have to do the research. But anyway, let's play around with this for the next 15 minutes. You can just mess around. Lots of data in there. And I'll give you some more guided instruction on Thursday. But just mess around a little bit.